Hello everyone, my name is Yujie. Today I will be presenting our work, CrossFS, a cross-layered direct access file system. This work is done in collaboration with Changwoo and Sudarsun Kannan. Modern file systems have several limitations. Some of them suffers from high software overheads, including system call compounded with underlying I/O stack. Though some new approaches are proposed to reduce software overheads, they lack support for leveraging compute power in both host and device. Host CPUs are fast, but processing I/O requests will result in low utilization, and device CPUs are underutilized. The last but not least, most of the current file systems have poor coarse-grained I/O level lock. Even accessing non-overlapping range blocks are serialized. To solve those issues, we proposed CrossFS, a cross-layered direct access file system. First, CrossFS disaggregates file system components into multiple layers, user level, OS, and firmware. Second, CrossFS provides direct access by passing OS kernel to reduce software overheads. Third, CrossFS provides fine-grained file descriptor level concurrency. Our evaluation shows CrossFS could achieve up to 4x higher throughput. Similar to the well-known memory hierarchy from processor cache to DRAM, now the storage is also becoming hierarchical. With the advent of new storage technologies such as nonvolatile memory, like 3D crosspoint and NVMe protocol for ultra-fast SSDs, the storage technology has finally entered the microsecond era. In addition to lower latency and higher bandwidth, modern storage devices are equipped with considerable compute power with multi-core CPU and DRAM. Now the performance bottleneck has shifted from hardware to software. To access a file on the storage, an application needs to issue a system call trapped into OS kernel. And there are several layers along the I/O subsystem in the Linux kernel before reaching the storage. During the above process, the following software overheads dominates: kernel trap and OS overheads such as locking inside OS. An I/O system call takes around 1 to 4 microseconds depending on system call type and data size. As we see, for all of the storage media, file system layer performance becomes very critical. Moreover, when applications are sharing files, increasing thread and process level concurrency is very important. In addition to hardware trend, application I/O behaviors also motivate the design of file systems. First, small random I/O dominates, not only in desktop but also server applications. The second trend is that concurrent file access is required. Not only multiple threads, but also multiple processes are accessing shared file concurrently. The third trend is that crash consistency is critical. Applications rely on file system crash consistency mechanisms. There are roughly three categories of file system design. KernelFS is a traditional file system design that put every file system components in the OS kernel, which managing both data and metadata. UserFS disaggregates data plane and control plane operations, where data plane operations are bypassing OS kernel, but control plane operations need OS trap or IPC between application and trusted FS server. FirmwareFS takes a radical approach that offloading the entire file system components to storage firmware to provide direct access for both control and data plane operations. However, there are several limitations of state-of-the-art file system solutions. Here, we list 4 properties discussed earlier: direct access, utilize host CPU, utilize device CPU, and fine-grained concurrency control. KernelFS suffers from high system call overheads, could not utilize storage compute resources. UserFS, while it provides direct access for data plane operations, but it cannot able to utilize storage compute resource. FirmwareFS, it provides direct access for both data and control plane operations. Even though it takes full advantage of storage CPU, it cannot use powerful host CPU resource at all. We notice that none of the above approaches are able to utilize both host and device compute resources, and they are limited by coarse-grained concurrency. CrossFS satisfies all of those 4 properties. Now let's take a close look at what is happening in file system for file sharing. Let me give you a simple example. There are 2 threads accessing a shared file. As we know, for each file, there's an inode structure in the file system. Even if thread 1 accessing block 2 and thread 2 accessing block n, once thread 1 holds the inode level lock, thread 2 need to wait until thread 1 write to block 2 and then release the lock. Only after thread 2 get the lock, thread 2 could write to block n. To analyze the impact of inode level lock, we perform an experiment that concurrent reader and writer threads are randomly accessing a shared file. We compare 3 types of file systems: kernel-FS, user-FS, and firmware-FS. As the number of threads increases, the aggregated throughput does not scale very well. As we showed in the previous slides, they are limited by inode level lock. However, CrossFS is able to scale because of fine-grained concurrency control. To break the limitation of current file systems, we propose CrossFS, a cross-layer direct access file system. In contrast to state-of-the-art solutions that disaggregate control plane and data plane I/O operations, CrossFS disaggregate file system components into different I/O software and hardware layers to exploit host and device CPUs. CrossFS bypass OS to reduce software overheads, and CrossFS also introduces a file descriptor-based fine-grained concurrency control, a firmware-level I/O scheduler framework, and finally, a cross-layered crash consistency mechanism. CrossFS disaggregates file system components across I/O software and hardware layers. The kernel component is responsible for file system mounting, setting up I/O queue region, and security. LibraryFS with each application that utilizes host CPU, providing POSIX semantics, adding I/O commands to the I/O queue, and also perform fine-grained concurrency control. FirmFS runs inside storage device, utilize storage CPU, scheduling I/O requests from I/O queue, and also traditional file system functionalities like data metadata managing, journaling, and permission check. CrossFS provide direct access bypassing OS kernel and only go to the kernel component when necessary. To illustrate, here's a simple example. When an application calls a write system call, LibraryFS converts the system call to firmFS I/O commands and insert the request to the I/O command queue. Later, the firmFS fetches the I/O command from command queue, and before processing, firmFS will perform permission check. Now let me introduce the fine-grained concurrency control in CrossFS. As we analyzed in previous slides, inode level reader-writer lock is the bottleneck. Even non-overlapping reads and writes are serialized. Hence, non-overlapping writes could be in parallel. We observed that different threads could open different file descriptor for shared file. For this example, 2 threads opens the shared file, but they use their own file descriptor to issue write requests. So, file descriptor is a natural concurrency abstraction that different threads or even processes have their own file handle for a shared file. CrossFS aligns each file descriptor with a dedicated I/O queue. We know this as FDQ. Here's an example of 2 threads are accessing a shared file. When thread 1 calls open, it will reserve an FDQ created by OS component in NVM region. Similarly, thread 2 gets its own FDQ. The write request come from thread 1 will only go into FD1's FDQ, and the write request from thread 2 will go to its own FDQ of thread 2 without interfering with thread 1. You might immediately find out that, what about overlapping concurrent writes? Now let's recap the previous example that, what if the 2 threads are updating overlapping range of 0 to 4K? As our file descriptor-based concurrency, those two overlapping updates are inserted to their own FDQs. So the question is which one to dispatch in the firmFS and which one is the latest one to choose. To resolve the overlapping updates, CrossFS used the interval tree data structure. The interval tree is an augmented self-balanced binary search tree. As is shown in the figure, each node has an interval with the low value and the high level of the interval, and also the max value in the subtree to help lookup and insert operations. Interval tree provide efficient lookup for overlapping block requests according FDQs. We use interval tree to store I/O block ranges for in-flight requests. Here's the example of how the interval tree helps resolving overlapping writes. As we described earlier, each inode has its interval tree in the library FS. In operation 1, thread 1 calls pwrite ranging from 0 to 4K. Library FS lock the interval tree, insert the entry of 0 to 4K range with the atomically retrieved timestamp counter into interval tree node, and then release the lock, and finally put this IO request to its own FDQ. Similarly, in operation 2, thread 2 calls pwrite ranging from 4K to 8K, which is a non-overlapping request. After insert the range into the interval tree and unlock the tree, library FS put operation 2 into the FDQ of thread 2. Operation 3 is an overlapping update with op1, as both are updating range 0 to 4K. When library FS is looking up the interval tree, it finds out that an earlier request op1 is overlapping with op3. Hence, the library FS updates the interval tree node and then insert op3 into the queue of operation 1 because they are overlapping. In this example, operation 1 is marked as no op because op3 is the latest version of range 0 to 4K. By using interval tree structure, the lock is only required in the interval tree lookup, insert, and delete. However, for traditional inode level reader-write lock, it needs to be held until the request is finished. The critical section is really short in CrossFS. CrossFS converts file concurrency control to queue ordering problem. Once the requests are ordered, firmFS dispatches requests from FDQs in parallel. Now the question is, how could we dispatch and schedule FDQs efficiently in firmFS? There could be hundreds or even thousands of FDQs in applications, while there are only few in storage CPUs are available. To solve this problem, we propose a unified firmware-level IO scheduler to map FDQs to firmFS processing threads, separating scheduling mechanism with policies. In CrossFS, we currently implement two policies. The first one is round-robin policy that each device CPU dispatches requests from one FDQ in a round-robin fashion. It provides fairness, but could potentially delay blocking operations like read and fsync. Because in CrossFS, write operation happens asynchronously, it is appended to NVM FDQ and data buffer before processed by firmFS. To remedy this problem, we implement an urgent-aware scheduling policy that prioritizes blocking requests like read. But to avoid infinitely delayed write operations and free space for FDQs, we set a delay limit for each write request to avoid starvation. In our future work, we will exploit more sophisticated policies according to multiple I/O patterns from applications. CrossFS also provides cross-layered crash consistency. Due to time limit, please see our papers for more details. We evaluate the actual benefit and efficiency of CrossFS, and we set up a set of experiments. We use a dual-socket 64-core Xeon processor with 512GB Intel Optane NVM as our storage. Due to the lack of programmable storage hardware when implementing CrossFS, we evaluate firmFS as device driver in a Linux kernel. We reserve kernel-level threads as dedicated device threads handling I/O requests, adding PCIe latency for every I/O operation, and reduce CPU frequency to match device CPU speed. We compare CrossFS with state-of-the-art kernel-FS, ext4dex and Nova, user-FS, Strata and Split-FS, and firmware-FS, dev-FS. Our first evaluation goal is whether CrossFS could achieve concurrent access scaling when sharing files. We developed a microbenchmark that multiple readers and for writer threads randomly accessing a 12 GB shared file. The x-axis shows the number of reader threads, and the y-axis shows aggregate reader throughput. As number of reader thread increases, ext4dex and Nova suffers from system call and INO level lock overheads. dev-FS removes software overheads, but still suffers from high coarse grain lock overheads. Split-FS and Strata avoid system call overheads, but still limited by INO level lock. By removing INO level lock and providing direct access, CrossFS shows up to more than 4x throughput gain for reader threads. Then what about concurrent writers' performance? We use the same set of benchmark and evaluate writer throughput. Y-axis shows aggregated writer throughput. Similar to the reader's performance, CrossFS shows up to more than 3x throughput gain for writer threads. That's because for non-overlapping writes, they could be dispatched in parallel thanks to the fine-grained concurrency control in CrossFS. We next studied the performance breakdown with the same microbenchmark of 16 threads of readers and 4 writer threads. We studied the breakdown of CrossFS by enabling each feature one at a time. Our baseline is CrossFS IOPT lock, which means using IO control system call for issuing IO requests and coarse-grained INO level lock. With our descriptor-based concurrency control with interval tree, kernel bypassing using shared IO queue between library-FS and firmware-FS similar to IOU-ring interface in recent Linux kernel, and urgent-aware scheduling policy, CrossFS could achieve more than 2.7x and 2.5x for reader and writer respectively. We then studied the IO scaling without file sharing using a well-known macro benchmark, Filebench. For write-heavy workload file server, CrossFS is able to achieve more than 2x throughput gain because CrossFS writes to NVM buffer first and then asynchronously dispatches requests, hence achieve high throughput. Our final evaluation goal is that could CrossFS benefit real-world applications? We select RocksDB, a well-known IO-intensive key-value store. We evaluate the random write performance with dbbench. CrossFS is able to achieve more than 2x throughput gains because RocksDB threads append key-value pairs to shared log files, and CrossFS eliminates inode level log overheads. To summarize CrossFS, motivated by high software overheads and poor coarse-grained concurrency, in current file systems, we propose CrossFS that disaggregate file system components into multiple layers, a file descriptor-based concurrency control, and a unified firmware IO scheduler framework and cross-layered crash consistency. Evaluation shows CrossFS could achieve more than 4x throughput gain in microbenchmark and 2x in application. To conclude today's talk, storage hardware has reached the microsecond era. Providing direct I/O and utilizing both host and device level compute is critical. Also, fine-grained concurrency control is important for I/O scalability. Our future work will focusing on supporting sophisticated scheduling policies and other file system operations. Thanks for your attention.